Hello students, welcome back. And now let us talk about step response of RL circuits. That means I have one resistor, one inductor and some voltage or current source is still present in my circuit. So here again we will take the exactly same approach that we can apply KVL and we can solve for I of t. So when we are doing it, we are applying the KVL here. So we will again get a very similar equation. That means the current in the circuit, which is series current of R and L, is I infinity plus difference of I initial minus I infinity into e raised to power minus t by tau. So that means our focus is again finding three parameters: initial current I0, final current I infinity, and time constant tau. And time constant for RL circuits is L by R. So once we have these things, we can solve any circuits. Now let us take a little complex circuit which is here. So I can see there are two switches, which is S1 and S2. One switch is going to close at t equal to 0 and one will close at t equal to 4. That means initially both of them were open. When this switch is open and when this switch is open, so we can see that there is absolutely no current which can go beyond this point or no current from this source beyond this point. So that means the initial current in the inductor is 0 because none of the voltage sources, either this or this, they are connected to this inductor. So we are fine. Now let us assume that only S1 is closed, S2 is not there, it is still open because it is t equal to 0. We have not reached t equal to 4. So S1 is closed, that means it is still open. So that means this is out of picture, this is out of picture. And now I have this series circuit and assume that for infinite time this combination will remain. So if this combination will remain, that means 40 volt, 4 plus 6, 10 ohm and 5 Henry. Then what will be my I infinity? Okay, that will be 40 divided by 10, 4 ampere. And what will be tau? Tau will be L by R. What is L? L is 5. What is R? 4 plus 6, 10. So I got tau also. That means my equation for t greater than 0 is I infinity plus I initial minus I infinity e raised to power minus t by tau. So I got this equation. Now this equation should have survived from 0 to infinity because that is our assumption. But at t equal to 4, another source is attached and that means we will have to truncate this equation at t equal to 4. So that is why it is from 0 to 4. Now at t equal to 4, what is the value of current? If I put t equal to 4 in this circuit, then I can find that 4 into 1 e raised to power minus 8, it is 3.997 something, which is almost 4. That means the current at t equal to 0, which was 0, at t equal to 4, it has reached almost 4 ampere. Okay, fine. Now at t equal to 4, what we are doing, we are providing this excess also. So that means now this total current will be combination of this effect plus this effect. So we are going to calculate our I infinity again. And that I infinity is 2.727. And for this circuit, what is our R equivalent for this inductor? Now if you see, to find R Thevenin, I will make this as short circuit, this as short circuit. That means 4 ohm is parallel to 2 ohm and whatever is their total combination, that is series to 6. So that means 4 ohm is parallel to 2 ohm and series to 6. So 22 by 3 is R Thevenin, L is 5, so tau is 15 by 22. So what will be my equation for t greater than 4? That will be I infinity plus I initial, initial means I4, minus I final e raised to power minus t minus 4 by tau because it is for t greater than 4. So I infinity is this. We just calculated here. Okay. I initial at 4 is this. I final is this. And this is our equation. So now my final answer is that for t less than 0, it was 0. For t between 0 to 4, it is this. And after 4, it is this. Now, if anyone asks me any other parameter, that how much is the voltage across this or how much is the voltage across this, then we can find it appropriately. So friends, that is how we handle the step response of RL circuits. Keep learning. Thank you.